Ah, really? Okay.
Okay, folks, welcome to this session on the final day of the conference. It's a great pleasure to introduce Marco Corgini Videla from the Department of Mathematics at the University of La Serena in Chile.
Thank you. Well, I'm going to talk about Bose-Einstein condensation, not from, I am a mathematician, not a physicist. And I would like to introduce you some basic concepts, some thoughts. First, this is a phrase of Barry Simon. It's the relationship between mathematics and physics. Mathematical physics is a borderline discipline between physics and mathematics. So I would like to read it. The techniques used and the general approach to the subject have become more abstract in any area of physics and mathematics. These developments have had various serious effects, not the least of which is the difficulty of communication between mathematicians and physicists. Physicists are often dismayed at the breadth of background and increasing mathematical sophistication which are required to understand the models. Mathematicians are often frustrated by their own inability to understand the physics and the inability of the physicists to formulate the problems in a way that mathematicians can understand. So, I'm going to try to explain some of the problems of Bose-Einstein condensation as phase transitions in the framework of this theory, thermodynamic limit, etc. So, thermodynamic limit and phase transition theory. In classical and quantum equilibrium mechanics, phase transition, PT, are associated to the non-analyticity or singularities of thermodynamic functions in the so-called thermodynamic limit, consisting that the density of particles remains constant while both the number of particles and the volume of the region enclosing them tend to infinity in a suitable way. Excuse me. This limit, whose introduction was suggested by Kramer in 1934, was applied by Lars Onsalier in 1944 for exactly solving the two-dimensional Ising model. The early Ehrenfest classification of phase transitions, based on the lowest order of some derivative of the free energy presenting discontinuities, was extended or modified to include notions such as ordered parameters and broken symmetries. The rigorous mathematical approach initially developed by Markov and Nikolai Bogoliubov received further impulse from works of many mathematicians and physicists during the 60s and 70s of the last century decades. Among them, Barry Simon, Leib, Spencer, Froelich, etc. This approach has been extensively used for studying, among others, superfluid and superconducting ferroelectric phase transitions. On this conception lies the basis not only of the Landau theory of continuous phase transition, but also the Lee-Yang and renormalization theories, including all mean field strategies developed during decades. So, what are the main approaches here? We have three approaches. The approach of the grand canonical ensemble systems, so macroscopic system, I mean. Canonical ensemble, arbitrary but fixed number of particles enclosed in some regions of the space, and the microcanonical ensembles with a few amount of particles. Microscopic Hamburg theory or macroscopic theory. A microscopic theory connecting the asymptotics of the order and disorder phases across the critical regions has not been found yet. This is not necessary. So, what's the framework, the theoretical framework, the initial theoretical framework to explain from the point of view of the operator theory, to explain Bose-Einstein condensation. So we have to start with one particle free Hamiltonian. This is the Laplacian enclosed. This represents the free energy of one particle enclosed in some regions. The set of accessible states is typically a Hilbert space. This L2 lambda L. Lambda L is a region, typically a cube. Maybe you can choose another kind of region. This is the cube, for example, in RD. Cubic box of boundary delta lambda L and volume BL. Okay. This is the dimension of D is the dimension of the space. Under suitable boundary conditions under which SL becomes a self-adjoint operator are assumed. So you have a countable set of eigenvalues depending on the boundary conditions, and a countable set of orthonormal eigenfunctions or accessible states for the systems, stationary states. So we are working with bosons. Bosons are represented by symmetric wave functions. So we have to construct for a system consisting exactly of n particles a new Hilbert space consisting exactly of this amount of particles in this way. SB is the symmetrization operator. FB is the Fock space constructed on the basis of the original Hilbert space, H, and is constructed to study a system of arbitrary number of particles. We have to introduce the operator of creation and annihilation of particles, which satisfies these commutation rules, well known. And any operators in these formulas, which can be written in terms of the operator of creation and annihilation of particles, is written in a second quantization form. So HL now written in this formalism is a self-adjoint operator now on the Hilbert space FB, the Fock space. HL has a free part, H0, which represents a system without interactions, and HE I represent a system with the interaction in the system. Beta is the inverse temperature, and mu the chemical potential is a real variable. So the second quantization of the Laplacian, in other words, the free Laplacian, in other words, the system without interaction is this, in the first line, in the first row, and the interaction has this form in interaction between coupled particles, for example. N is the number of particles associated to the state G. N is this sum is the total number of particles in the systems. And HL mu, for definition, is HL minus mu n. And the main thermodynamic functions in the finite systems are defined in this way. This is the trace taken over the Fock space, and HL mu is the Hamiltonian defined before. We have here a number of, this is a finite system. We are not moving yet the volume. And zeta n is the canonical function, canonical thermodynamic function. Is defined on HNB. So this is the Hilbert space for a system consisting exactly of n particles. Okay, and this is a restriction of the operators H to a system of exactly n particles. The free energy is defined in this line. This is rho L is the in the canonical representation. So in the system with a system of exactly particles. And finally, the pressure for the grand canonical system is defined in this way. I know you know what this these things. The given states and the grand canonical representation is given in this way. A is any operator defined on the focus space. Okay? This is a kind of average of operators. Generally speaking, we are looking for operators which are commuting with the total number of operators, so satisfies this commutation rules there. It implies some kind of invariance under U1 group. This we can make in the Hamiltonian this variable change, and it implies some selection rules which are defined here. Okay, so the average of the creation operator associated to the index P, or the annihilation operator associated to the index P is equal to 0. So all this derived from these commutation rules. What we mean by Bose-Einstein condensation in this framework? If we take the average of the number of particles associated to the minimal energy state in the system, and 0 over PL, which is the volume, take the thermodynamic limit VL tending to infinity, then this amount has to be greater than 0 when the density of the system is larger than critical density rho c. We can broke the symmetry by adding this term there, for example. In this case, the neo operator HL nu, does not commute anymore with n. So the selection rules we had before are broken. So remember, we have this here and this here immediately. Okay. What we mean by broken symmetry? Broken symmetry is obtained when this limit is not equal to 0. So when the average of the average of A is 0 now, so the creation and annihilation particles operators associated to the minimal energy system over the volume tends to number not equal to 0. In the non-condensate phase, we can prove that it's possible to exchange these limits, and in this case, it is always 0. So in the case when the critical density is satisfies the second rule inequality there. But anyway, this is a macroscopic occupation of the ground state of the system. Okay, but anyway, we can verify in any case, for example, macroscopic occupation of other states close to the ground state. For example, this is the relation in these cases. So, all our system will have to consider that the density of particles is a constant of the systems. These are the free energy, limit-free energy in the thermodynamic limit. This is the pressure in the thermodynamic limit too. The general Hamiltonian has this form here. So this Fourier transform of potential of interaction between a couple of particles, for example. This P prime represent momentum, etc. So we have three types of condensation. Condensation of the type 1, macroscopic occupation of a finite number of states. including ground state, condensation of type 2 holes when there exists an infinite number of states macroscopically occupied, a condensation of type 3 or generalized big holes when there are not macroscopically occupied states, but the following condition holds there. This is the weakly interacting Bose gas. So what kind of methods we can use to try to solve this problem? Approximating Hamiltonian methods, light deviation methods, infrared bound methods, etc. What the difference with magnetic traps? So we have here a graphic for magnetic trap, optical traps, and by using experimental techniques of laser cooling and vaporization, we can lower the temperature for a cloud of atoms in the magnetic trap and obtain Bose-Einstein condensation. What's the difference between the theoretical results obtained before with this kind of models? Travel systems are mesoscopic systems, completely isolated finite systems do not exist. Trappist gases are finite-sized systems. The number of atoms can be put into the trap cannot be considered macroscopic. In the framework of the standard theory of phase transition, big and the corresponding breakdown of U1 symmetry exists only in the so-called thermodynamic bulk system, or at least step system. In the presence of a significant condensate, interaction effect becomes determinant and dominates this region of temperatures. In this scenario, the Bose-Einstein model does not describe adequately the system behavior. Trapped systems are spatially inhomogeneous, at least until 2013. Beck in acoustic with a demonstration of Beck in a quasi-uniform 3D-dimensional potential of an optical trap box. Trapped Bose gases can display low-dimensional Beck in a mesoscopic sense, phenomenon provided for infinite particle systems. This is a quasi-two-dimensional. The thermodynamic limits never reached exactly, and to overcome the difficulties in defining pressure for a gas confined in an inhomogeneous trap, it is necessary to define simple macroscopic parameters that behave like pressure and volume. So we have the model of a Bose gas, ideal Bose gas in harmonic trap. So this is the geometrical average. And the relation between the number of particles in the condensate and the total number of particles as function of temperature and critical temperatures is this one. And in this case, we have to take a kind of thermodynamic limit defined there. So we have to open in some direction the harmonic trap. In the case of the ideal uniform Bose gas, we obtain in the classical framework, we obtain rather different results. Anyway, we have to define, in the case of harmonic traps, harmonic volume. Harmonic is an effective volume. It's not exactly a volume. And we have some interesting results from a theoretical point of view due to Tamura and Zarianov for a rather general model of harmonic trap with weak trap limit defined in this way. On the other hand, we have also uniform condensation in trapped Bose gases. Conventional many body systems are spatially uniform. Ultra-cold gases, trapped gases do not represent transnational symmetries. Atomic Bose-Einstein condensates have been obtained for linear or circular traps which are uniform along only one direction while still being harmonic along the other two. However, Bose-Einstein condensation of an atomic gas in a quasi-uniform potential was observed and characterized quasi-uniform box systems. both the momentum distribution of the non-condensed component and the thermodynamic of condensation are close to the theoretical expectation for a uniform system, while being clearly distinct from the conventional case of harmonic eccentric gases. This is the so-called textbook example for Bose-Einstein condensation. Some words about the microcanonical approach. The microscopic theory, which should connect the asymptotics of the ordered and disordered phases across the critical region, has not been found so far, even for any one of the numerous phase transitions. It's not so only for Bose-Einstein condensation. The main objective of microscopic theory is to calculate the large contribution of the lowest energy levels to the critical fluctuation, to avoid infrared divergence of the standard thermodynamic limit approach, to resolve a fine structure of the lambda points. So there are some works due these guys. I want to finish here. Kocharovsky, Holtons, Raymond, Owen, and others, et al., who developed a procedure to treat this kind of models from a point of view of the canonical ensemble. It's a very interesting thing, and it's an alternative to other kind of procedures without using traditional thermodynamic limits. It's new results. That's all.
Thank you very much. Any questions?
Too much information.
Is there any? Viv, would you like?
This is the stuff my colleagues do. I don't do this personally. I'm very familiar with the mathematics and their talks and so on. But they mostly, and they do analytic stuff, but a lot of the progress is being made with numerical simulations. Their experiments are done in my group as well. So it's not, they have the experiments to work with too. So, in a sense, what's the philosophical point you're making from this? I mean, the physical intuition.
I have 3 days here. Yes, I understand. I have three days here, so I have the impression, the feeling that there is thermodynamic limit levels and non-numbers. It's a very strange situation because I don't know anyone who a physicist, I mean, or mathematician, which considers the thermodynamic limit something like a religion. This is an approximate method. I'm trying to put the standard theory, mathematical standard theory, in connection with the new results. I'm saying that, in fact, there is connection at mesoscopic level. You have new phenomena which disappears in the thermodynamic limit. For this reason, it's necessary to develop further microscopic theory. But in the bulk systems, the thermodynamic limits serve us to approximate, not very close to the critical points, fairly well the phase transitions. So the problem is in the critical regions. And even the renormalization theory is not a good instrument to describe, in this case, the behavior. So for this reason I mentioned the works of these guys, because they are not using renormalization techniques to study these critical points. So they are using canonical ensemble approaches.
Okay, just a clarification question, and the other maybe a question. In one word. So what's your point about the thermodynamic limit? Do you think?
No, the thermodynamic limit. I'm open-minded in the sense that the thermodynamic limit is in fact a good approximation for real systems in some cases. In other cases, not a good approximation.
Okay, so I perfectly agree. And I just would like to know if you know Bormann theory about
Bormann.
No, Bormann. It's a theory that study phase transition based on the distribution of zeros of canonical.
They do that.
And because this is I think a theory about finite phase transition form was a session, and
yeah.
really don't need
I don't know this word, but it's very close to
okay, so
to the yes. Yes.
Any other questions? Well, in that case, let us thank our speaker.